Okay, this go round we're going to be looking at bonding, and we're going to start out part one here with ionic bonding. So first up, let's think about why elements would want to bond in the first place. And a lot of it has to do, if you can think back to that Bohr model, that outermost shell or energy level, the valence shell, it wants to have 8 electrons. Well, everything except for helium and hydrogen, when they do want to have 2 because their outermost energy shell only holds 2. But almost all atoms, all elements want to have 8 electrons, and they call this the octet rule. Because if you remember those noble gases, they were very stable. And they were very stable because they had a full valence shell. So the octet rule means that no matter how many electrons they have in their outermost valence shell, they want to try to get a full one. So that means you'll have elements giving off or taking in an electron in order to get to that. So here's an example of one such case. So we have sodium that has 1 electron in its valence shell. And we have chlorine that has 7. Now sodium, if it gives 1 off, that shell goes away and you use the previous shell, which is completely full in sodium, as its new valence shell. Because of that, that would make sodium stable to give 1 away, and chlorine, it only needs 1 to complete its set of 8 now. So it wants to take 1 in because that would go ahead and do it. So simply think, look, what's easier, to get rid of a few or to take a few in? And it gives you an idea of what they want to do, whether they want to give away electrons like sodium or they want to take in electrons like chlorine. So essentially, chlorine steals an electron from sodium and we get sodium chloride, which is table salt. Basically, the important thing to remember, though, is you're making 2 different ions, and it's not shared. That's something completely different from ionic bonding. Is in this one, they don't share the electron, but we do get ions. So ionic bonding occurs between a metal and a nonmetal. Well, it usually occurs. I say usually because it can involve things like metalloids for a few little things, but not a ton. Normally, you can simply say a metal and a nonmetal. If you want the very technical term, it has to do with the electronegativity, and that's how likely it is to become an anion or a cation, which is what we're talking about with ionic bondings anyway. The easier way, just look at your periodic table. Non-metals, all the rest of it else is metals. Pay no attention to your noble gases. So a non-metal with a metal, that's an ionic bond, almost always. So let's take a closer look at what's going on. You're forming 2 ions, thus ionic bonding, because you're creating a cation and an anion. Remember, cation is just a term for a positive ion, meaning it gave away an electron. If you get rid of a negative, you're going to be positive. So sodium in this case gives away the electron and is going to be our cation. Anion is a negative ion, meaning it took on an extra electron. Chlorine takes on an electron, and so it becomes the anion. Once again, we can break ionic bonding down to 3 basic steps. An electron leaves one atom, goes into another atom. That creates a opposites attract type deal going on, also known as an electrostatic force that pulls them together. So positives and negatives attract, if you didn't know that. That's groundbreaking, I'm sure. Now, this happens between any that want to give away an electron and want to take in an electron, between a metal and a nonmetal. So anytime you get a positive and negative, but it does create a very weak and easily breakable bond. We can tell this because if you put salt, table salt, sodium chloride, in water, it completely dissolves, or dissociation. Complete dissociation, meaning it completely breaks up into its compounds of sodium and chloride again. Now, that means it's a fairly weak bond. So our big problem so far is we've just looked at things like sodium that has a +1 and chlorine, which has a -1. Well, of course those two are going to go together. They just trade a single electron, right? But we almost never look at single atoms to begin with. We look at a big old pile of sodium and a big old pile of chlorine, and that's just what they need in order to make that. So now we need to work it out to where we can figure out how other things might bond together that don't perfectly match giving one electron over. Sometimes you might need more of one atom than you do of the other. So what we look at instead is our oxidation number. And notice I'm not looking at transition metals right now, just my alkalis, my alkalines, and my halogens, and some of the other ones. Okay, so remember, these are noble gases. They don't react at all. These columns, though, and this is what we mean by 1A, 2A, 3A, 4A, 5A, and so on. But these columns are what tell us those oxidation numbers, and they tell us how many we're going to need of each. So something in our alkalines is going to need to give away 2 electrons. Things over here in our halogens will only need to take in 1 electron. So basically, you're going to take 2 of your halogens for every 1 of your alkalines in order to make a balanced combination. Okay, let's look at that a little more. And this is saying the same thing I just said with the periodic table. The only real important part here is your hydrogens. It has that just 1s valence shell, so it's 1 electron, puts it halfway between empty and full, meaning it can go either way. However, I will say hydrogen is mostly used with making acid, which we'll talk about later. Also, notice that the transition metals can vary. That's why we're not talking about them yet, though they are used in ionic bonds. So let's figure out how to use those oxidation numbers in order to help us make a new compound. The first thing we need to do is we need to write each of our elements. You need to write your cation first, and you're going to write out what their oxidation number is. So for magnesium, it's going to be a +2. For bromine, that's going to be a -1. Okay, so you write both of those. Then you're going to copy down your elements with that cation first still, and you're going to cross over. So I'm going to take this and cross over and make it a subscript. I'm going to take this and I'm going to cross it over and make it a subscript. Now, we're only making it, though, not negative and positive, just the numerical value, okay? So that's a 1 and that's a 2. Now, the reason we do that is so we get something brand new that we can put together, and we can say that this is now 1 magnesium to 2 bromine. However, there's another rule to where I wouldn't have written this 1 magnesium symbol if I didn't have at least 1. So I'm going to do away with writing the 1 because it's redundant. So let's just go ahead and rewrite this as magnesium bromide. And that's how you would come up with the correct compound. So after you have your bond form and you have your new compound, you have to name it. Now, these basic ionic bonds for just a metal and a non-metal, most basic form of the ionic bond, it's pretty easy. The name's going to end in an IDE. Now, when I say the name of it, that's the second element. Your anion is always going to be second, and it's going to end in IDE. So you just change it. So notice it's no longer chlorine, but chloride. Your metal, or your positive oxidation, or your cation, as you need to learn it, is going to come first. You can use the group oxidation number for most nonmetals to figure out if it's positive or negative. Do not capitalize unless you start a sentence. And so some examples we have of this are calcium and sulfur. You end up with calcium sulfide. Potassium and bromine, you end up potassium bromide. Sodium and oxygen, sodium oxide. We're going to practice a few, but notice this is the correct formula and the correct name for each of them, and that's what you got to learn to do. All right, so let's work these out from beginning to end. Here I have 2 elements, a metal and a nonmetal, magnesium and nitrogen, and I'm going to be able to make an ionic bond with these 2. So first thing I need to do is I need to figure out their oxidation number. To do that, we look on the periodic table, and as you can see, magnesium is here in the second 2A row. or column, and it's going to have a positive 2 oxidation number. Nitrogen is over here in the 5A column and is going to have a negative 3. So let's go ahead and put those down for those. We have positive 2 for magnesium, negative 3 for nitrogen. And then we're going to start by rewriting our elements. Steel cation first, anion second. We're going to bring down those oxidation numbers to subscript for the opposite element, but lose the charge. So that means a 2 here, 3 there. And then we're going to rewrite it all nice and pretty. So I'll do like that, because this doesn't reduce. So 3 magnesium to 2 nitrogen. And that's what that means, that I have 3 magnesium atoms to every 2 nitrogen atoms to form this compound. Now, what is this compound called? Well, that's where we need to do the naming so that we get things. We're not going to capitalize, but we're going to write magnesium just as it appears on the periodic table. And yes, I am looking at a periodic table in order to copy that down. Then we're going to change nitrogen from nitrogen to nitride. Notice that IDE ending. And that's going to give us our new formula in its proper name. Magnesium nitride is made of 3 magnesium, 2 nitrogen.